guys, welcome back. Today we're going to be talking about potential energy. Now again, we said potential is going to be opposite of kinetic energy, and kinetic energy was energy in motion. In this case, we're going to have energy not in motion, which is going to be stored energy, or something that has the ability to have energy, or to have kinetic motion. So potential energy, well, there's two types. You have gravitational potential energy and you have elastic potential energy. Gravitational obviously has to do with gravity. You know, so if everything that goes up comes down, has the potential to become kinetic energy. Up here, it doesn't have any kinetic energy unless I drop it. Now, that's going to be gravitational. The other one is elastic potential energy, and that has a specific word next to it that says stretch. Now, we're talking about things that stretch. We're talking about things that springs, rubber bands, those kind of things that when you pull them apart, they come back together. Well, each one is going to be a little bit different, but we'll get into more on that here in just a minute. First, I want to talk about gravitational potential energy. Now, gravitational potential energy, like I said, has gravity, and is going to be signified by the equation PE, gravity, is equal to mass times gravity times height. Well, we'll go through each one of these like we did in the last video. PE simply stands for potential energy, and just like all energy, we look at it in joules, and how we measure it's going to be in joules. M is mass, so how much mass the object has. G, gravity, 9.81, and then height we measure in meters. So let's look at number one first. Number one here, it says a 45 kilogram boulder sits on the edge of a 30-meter high cliff. How much gravitational potential energy does it have? Fun stuff. Let's check it out. Let's pull out the information first. 45 kilograms. Well, kilograms, we know that's going to be mass. So mass is going to equal to 45. Boulder sits on the edge of a 30-meter high cliff. Height, meters. That's going to be height. So that's going to be 30. And we know that gravity pulls at a constant 9.81 meters per second squared. So how much gravitational potential energy does it have? So we'll plug it into our equation where it says PE equals 45 times 30, or 45 times gravity, which is 9.81, multiplied by 30, because that's our height. Multiply all these together. We'll go ahead and do that with you. So grab your calculators, type in 45, multiply that by 9.81, and multiply it once more by 30, and you'll get a very, very large number. So potential energy becomes 132,000. Oh, sorry, there's a decimal there. 13,243.5. And again, PE, potential energy, we measure that in joules. If you wanted to do it the triangle method, I have the triangle way set up right over here. So this PE goes on top, then you have mass times gravity times height. Now this looks a lot different than some of the other triangles that we've done because there's not 2 on the bottom and there's 3. Well, all we're doing for this is we're simply taking what we know, or what we're looking for, out of the triangle, and we're plugging in the rest of it. So PE is going to equal mass times gravity times height. So mass was, we said, 45, multiplied by 9.8, multiplied by 30, multiply all those 3 together, and you'll get the same 13,243.5 joules. Now we're going to go and back up and talk about elastic potential energy. Now elastic, like I said, has to do with things that are stretching, things like springs. Now if you take a look here, I have this handy dandy fun little slinky toy. Fun for boys, for girls and boys, all that good stuff. Now every slinky has potential energy whenever it's stretched out. Because whenever I stretch it out like this and I let it go, the energy snaps back at it. So the more I stretch it, the more potential energy that it'll have. So let's go ahead and see what kind of equation we use for this one. This equation is going to be this one right here, where PE elastic is equal to 1/2 kx squared. Well, there's some new variables in there for us. K. Well, what is K? K is going to be our spring constant. Now, like before, the word constant means unchanging, never changing. But in this case, it's going to vary by the spring that you use. So this spring here, this slinky right here, is going to have a much different constant than, let's say, the spring on the inside of a stapler. The stapler will have a much lower constant. But each one, if you know the constant, is going to be the same for that spring throughout its lifetime. And X, so we said that K was our constant. X is nothing really different. It's just a new way for us to put distance. So we're going to square our distance in this. So PE elastic equals to 1/2 kx squared. If we wanted to put this in triangle form, PE elastic is equal to, actually we just do it right down the middle. 1/2, we said 0.5 k and then x squared. Now let's go ahead and use this information that we know and plug it into this equation here. It says the staples inside a stapler are kept in place by a spring with a relaxed length of 0.115 meters. If the spring constant was 51 Newton meters, how much elastic potential energy is stored in the spring when its length is 0.15 meters? So there's a few things we can go ahead and figure out here. The first thing is I want to pull out that our spring constant is 51 Newton meters. So K is going to be 51 newtons over meters. Now we have two lengths given to us. We have two meters. We have a relaxed length and we have a stretched length. So we have two, but we only have one place to put it in. So we need to go ahead and make this number one number. And to do this, we'll take our stretched length at 0.150 and subtract our relaxed length from it. So 0.115. 0.035. So now that we have that information, we can go ahead and plug it into our equation, where we said potential energy elastic is going to equal to 1/2 K, which was 51, x squared, which was 0.035 squared. Let me grab our calculator out once again, and we'll plug this in together. Open parentheses, we'll do 0.5, close parentheses, multiplied by 51, and then once again multiplied by 0.035 squared. And when we do that, our potential energy for elastics is going to be 0.031, and that's going to be joules, because again, energy is joules. But if we wanted to put it into our triangle form, we can go ahead and do that as well. I'll move the triangle over here, and we'll do it together. We're still looking for potential energy elastic, but we know that's going to be half of our K, and our K was 51, and then x squared, 0.035 squared. Well, half of 51.5 times 51 becomes 25.5, multiplied by 0.035 squared, that becomes 0.001225. Multiply those two together, and you get potential energy is going to be 0.031 joules. And that matches both sides. So it works this either way you use it. If you want to use the triangle method, or if you want to use the equation method, use whatever works best and whatever you feel most comfortable with. If you guys have any questions, talk to your neighbors, see if they know, and then if not, y'all come up to one of us, to the teachers, and we'll hopefully explain it in a different way, something that you understand. Have fun, guys.